It's just actually a calculation here. It's just a linear correlation which gives you a value of your x naught. So you calculate your x naught location. That x naught comes across here, and that is your s naught. And s naught is used in the calculation for that section, for cy beta for the fuselage. Kind of follow that? So you got to know your configuration, your lock, your fuselage has to be defined to be able to get this value. And if you don't have a shape like this, that means your fuselage looks not like that. Yes?
So x1 is the inflection point?
X1 is the inflection point, yeah.
So what is x0 or x naught?
X naught is the calculation here. Zoom in a little more. So what you end up doing here, see that's x naught over LF. Well, you know your LF. So whatever this comes up with, when you have x1 over LF here, find that number, go up to the line, come across here, and that becomes, let's say it's 0.8. That's your x naught over LF is equal to 0.8. And then you just calculate the x naught from that. And then go back to your graph here, x naught, which they don't really define here, but that's what it means. You take that point and come all the way across here. That's your s naught. Yes?
How do you choose x1? I'm so sorry. Like
the inflection point.
Yeah, inflection point.
Let's see.
At one point you say this is that
Yeah,
point.
so see how this has got a positive. Oh, sorry. So you see how this goes this way, and then it sort of goes this way.
Right.
So when it changes curvature.
Also the point after you change its curvature?
Yeah.
Okay, that makes sense.
Yeah. That's where it goes from potential flow to like a turbulent situation. Yes.
So this is just for the fuselage, like, but what if we have the nacelles and stuff?
This is only for fuselage. Just stick with the fuselage. So you should have like a fuselage with nacelles on the side of it or something like that.
Yeah, but like it goes on to an empennage and has engine in it. It's really hopefully exactly.
Yeah.
So just fuselage.
Yeah, just fuselage.
All right.
And these are just estimates. This is something that your plane is going to go into the wind tunnel. You're going to get a whole bunch of data, and you're going to get your derivatives from that. So you're going to check it based on that. You know, this is good first cut. Yeah, you're definitely going to do all of that. All that later. Matter of fact, when you do wind tunnel testing, you'll probably have the cell on, the cell off. Do all those different configurations to get all that information. Yes?
Is this something that goes in the report?
Yes. Okay. So the way. Good question. In these PowerPoints that I give you, you want to follow what I ask. So if I say show all work, then I want to see all work. So in this case, show your version of figure 10.9 and 10.10. So this is 10.9, this is 10.10. Your version, meaning it's your configuration, your plane. So don't put that in there and use this view. Don't scan this in. I want to see this. I want to see that picture of your plane showing that information, okay? Follow me in that? All right, so it's your version of your plane. Vertical tail, same thing. Show your version of the vertical tail, and you'll look at figure 10.13, and you'll understand what I'm talking about there. That's just showing the plan form and all the definition. Rolling moment due to side slip. Well, you get a side slip, you're going to get a little rolling moment back, and you're going to have contributions to that. You'll have the fuselage. This has lots of figures, and yeah, I'm going to show it. Well, let's go over it. You're going to horizontal tail show all inputs and outputs. So you're going to have equation, yeah, all the stuff that goes into it, and what you're getting out of it. So I think we talked about that. You have a table of inputs and outputs. Show your version of, for the vertical tail, you show Roscoe 6 figure 10.27 on all your inputs and outputs. Go back to the document here. Here we go. Zoom in. So like this equation. So you can put that in there showing all your inputs and outputs. Figure 1027. I'll just show another example. I think I did this a few times. This one, I think it's regurgitated in a few areas. So the first time you show, let's say this, for one of your inputs, if you put your version in one place, you don't have to do it again in the rest of the time you use that. You just say refer to that section that you already put that in. CAD person should be able to do that. Do it to scale. Throw it in your report. So this is a fun one. Yawning moment to decide. So this is the one figure that I told you about, that you start here and you move up here and you go over here and then you move down here and you go over here, and each one has its own calculation to get that number. Yeah. So here I say use your aircraft geometry. So you're going to have a side view of your fuselage and your canopy, if you have one, and you're going to show all the dimensions for each one of these. And show me on this graph how you're coming to your final conclusion for your value. A vertical tail straight forward, I mentioned that, and CN beta wing, yeah, that's just 0. Luckily we're not doing high angle attack. Worry about that. Roll rate derivatives. I say here use Roscom for subsonic, and supersonic business jet must consult DATCOM. But I've already said supersonic business jet, you can do the subsonic version of all this. Unless you really want to do a supersonic version of all this, you can do that. But I'm not recommending downloading 3,000 pages of DATCOM to do it. Oh, here's the figure again. Previously determined this. For this one, be careful of some of your times your variables change up. This one is z sub v, that's the height here. But then all of a sudden they'll throw a z in here, and so you gotta watch out for them. They'll throw those tricky ones in there and mess you up. So it's a different z. This one's just to the CG to the wing root quarter chord. Rolling moment due to roll rate. Let's see. Yeah, wing contribution, your horizontal contribution, your vertical tail contribution. Pretty much straightforward, but in this one you want to show input and output of all contributions for these. Yaw moment due to roll rate. Equation 1063. This is another one I'm going to talk about. If there's one equation that you do not put in Excel first before you do it on paper, this would be it. You can see how easy something in Excel, you get your order of operations wrong and you get the wrong number. So if you can't get the right number and you don't have it on a piece of paper, make sure you get out a piece of paper and do it the old-fashioned way. Another one. 1065. Same routine. You can see where a lot of these things, for the people that are doing civilian control, if you don't have the data, you can be doing this in Excel already. You can have this all ready to go, and all you need to do is get some values, knock this out. From sweep to some of the other coefficients that you come up with. But it's all pretty straightforward, some of them, even though it's a long equation. How many have done this so far? Already jumped in. Not even one. Come on, nerds. Waiting for spring break. Pitch rate derivatives. Here's another. You're going to show your version of your plane. You probably don't have canards, but the rest of it you're going to want to show to get all those values for all your inputs. Put all the inputs in the contributions for that. Canard if you've got it. Here's another one. It's just a repeat. And there's another warning here. Watch out. Equations are big. You're going to mess it up if you're not careful. Yaw rate derivatives. Yeah, pretty much a repeat of the other. Some of these CY beta of the vertical, you're going to use it in multiple locations. You're going to find that. So as long as you got it in one place, you don't have to show the derivation of it again in your report. This one I'm asking for all inputs. This one, warning. In this section, the dihedral angle is in radians, but the wing twist is in degrees. Ask me how I know. Well, I screwed that up. I had to figure out, was trying to figure out why I was not getting the right value, and it took me a while, but I finally nailed it down. You pull out, a lot of times when the ROSCOM is not clear, I go to DATCOM. I go to the 3,000 page document and I look in there, and they usually have it. It clears up what I'm missing from here. Anyone try to download DATCOM yet? You did?
Looked at it.
Yeah. Okay.
There's no search function.
Yeah. Yeah, it really, I'm waiting for somebody just to go and take it and redo it. So that'd be a good, you could probably make a lot of money doing that, right? Put it back in a searchable format. Let's see, okay, very large equations. Yawing moment due to yaw rate. Wing contribution, show all the work. Graphs are based on distance from CG to aerodynamic center. I probably put that there for a reason because it may have been confused. So if you get confused, just go to here. If you're still confused, come talk to me. We'll figure it out. Vertical tail contribution is pretty straightforward. And then finally, you come up with your results. I like this. I've got this in my spreadsheet. I did this and it worked out pretty good. But I use Etkin. I like Etkin's format. I like Etkin's way to solve a small perturbation. So I get all the derivatives out of ROSCOM, and then I go to Etkin to actually do the analysis. It doesn't mean you have to use Etkin, but I know you are using Etkin for your stability and control class already. So, and Etkin is very weak in coming up with the derivatives. I think ROSCOM is really good. He's really done a great job taking DATCOM and giving you what you really need to know for this purpose. And then Etkin really shows you how to analyze it for your stability. So when you go to Etkin, you'll see CXU, CX alpha, CXQ, CX alpha dot. So all these are actually your CD. So all your CD, the CDU derivative, this is the CD alpha derivative, because it's X. It's in the X direction of your stability control axis. CZ is what? Lift, right? That's CLU, CL alpha, CLQ, CL alpha dot. CL alpha? Did I say CL? This is CL alpha. Your lift curve. Slope. So just so you know, that's the difference. Also, there's a little difference in the way the sign convention is. So you're going to find your CDU I think it's actually going to be the exact opposite. Same thing with here's CL alpha. Well, CL alpha is actually supposed to be positive, right? So just be careful on the way Etkin defines it. And I have another PowerPoint with dimensional derivatives that shows that. Any questions on that?